Rutherford had proposed that most of the atom is actually empty space, and almost all of its positive charge and mass are concentrated in a tiny central region, and electrons move around it. However, if the electron is moving continuously, it must lose energy and must finally fall into the nucleus. Without those electrons, atoms could no longer form chemical bonds. There would be no humans, no Earth, and no life that we know of. However, the universe is filled with stable atoms. So what keeps electrons from collapsing into the nucleus? This mystery was solved by Niels Bohr in 1913. Bohr combined two important developments. First, in 1900, Max Planck proposed that matter absorbs energy in fixed packets called quanta to go to higher energy states. The energy of each photon is related to the difference between the two energy states. This showed that energy could be exchanged only in specific amounts. Second, scientists observed that when we pass electricity in a discharge tube containing hydrogen and look at the image of it in spectroscope, it emits only specific colors in a discharge tube as we increase the input power. This revealed that the hydrogen can exist only at specific energy levels, including one fixed ground state and several fixed excited states. Bohr connected these two ideas to the Rutherford's model and said, inside an atom, electrons are allowed to occupy only certain fixed energy states around the nucleus. Bohr called these stable conditions stationary states. When an electron moves from a lower energy state to a higher energy state, it absorbs a photon. The energy of that photon is equal to the difference between the two energy states. Because only certain energy differences are allowed, only certain photon frequencies are produced. These different frequencies appear as the characteristic colors in hydrogen's line spectrum. The beauty of Bohr's insight is that atoms and molecules interact with light in distinctive patterns, almost like having their own spectral fingerprints. By studying the specific wavelengths of light that a substance emits or absorbs, scientists can identify elements and molecules present in distant stars and planets. Like helium was identified on Sun. One major limitation of Bohr's model was that he did not explain why a moving electron in a stationary orbit would not radiate energy. In search of this answer, the scientist realized that reality is actually very strange. An electron does not move along one fixed path. It can spread out and behave like a wave. But when we look for it, we find it at one particular place. How can reality be so strange? That is the mystery of the wave function.